So this is actually the tail end of our lesson from yesterday. I just wanted to say something about lines, and then I'll show you how this can generalize in a nice way in a minute here. Okay, so we'll start with this picture, and we're going to talk about how to generate a line in 2 dimensions using vectors. Okay. So imagine someone gives you points A and B. That is to say that A1 and A2 and B1 and B2 are not unknown. They are constants that someone has handed you. The goal that I'd like us to have together is to create a new vector, some vector, to the point P, which is an arbitrary point on the line. A and B are fixed. Points A and B are fixed. And point P is an arbitrary point along the line. And we're going to think of this point as, we're going to try and come up with a vector that points from the origin to this point P. So its component form we'll just call x comma y. Okay? So can we come up with a vector, OP, the red vector, using this point A and this point B that are known, that someone handed us? Well, let me highlight something you do know in this picture. You know these 2 vectors. Well, you don't necessarily know them completely, but you do recognize this relationship, don't you? That this vector OA, that is the position vector of A, that comes from the origin out to A, we could figure out what that vector is. And then I have this other vector highlighted too in purple, AP. Now what's the relationship, can someone tell me, between OA, AP, and OP? What's the relationship there? And the visual helps a lot. Yeah. It is a triangle, true. Thinking about things we've thought about recently though, what is the relationship? No. Sure, it's simpler than that, maybe.
If you add OA to AP, you get OP.
Bingo. Right? Do you see that OA plus AP is OP? Just end to end. Okay? Now, why would I bring AP into the mix? Well, what we have right now is, this is good. We said we wanted a vector OP that points to a generic point xy on a line. But what we haven't yet invoked is point B. We just haven't even mentioned it yet. Point B has just not been mentioned. But now we're ready to mention it. I don't know too much about AP, this vector that we highlighted in purple, but I do know that it has an interesting relationship to a vector I can get, and that's AB. What's the relationship between AP and AB? Is there anything interesting about them? The vector from A to B and the vector from A to P. What do you notice? Yeah, one is just a scalar multiple of the other. Yes? And notice the scalar I'm using. How about T? It's something times AB. Isn't that what AP is? So that suggests the following equation for the line in terms of the position vectors. The position vector A, OA, and what we'll call the direction vector from A to B. So if you know, if someone hands you point A and B, what we'd come up with is this little, what we might call the vector equation of this line. That is, it gives you a vector xy that points to a point on the line, an arbitrary point. You give me a t value of your choice, freely chosen t, and outputted, we get a point. We get a vector that points to a point on this line. So, t is arbitrary. So let's just be clear down here. X and y are dependent variables. T is your freely chosen independent variable. And A1, A2, B1, and B2 are all constants. They were all handed to us when we started the problem. We've given 2 points, A and B, that are on the line.
So T is the value that you put into the
Yep.
function?
Yep. And let's actually try plugging, even in this abstract form, let's try plugging in some values. Let's plug in t equals 0, for example. What happens when you plug in t equals 0? What is our vector xy when t is 0? It's just the position vector to A, right? This whole second part will go away. And if t is 0, then we just get a vector pointing to A. What if t is 1? clear?
Oh, that's the word.
No. No, I think you said it right the first time. What happens if t is 1? What happens if you add this to just one copy of this? That is OA plus one copy of AB. Where are we? We'll be at B, yeah. We'll have the vector that points to B, the position vector for B, right? So did you catch that? If t is 0, then our vector xy just points to A. And if t is 1, we point to B. What if t is 2? Well, I don't know where P is. It actually kind of looks like where it would be, right? P is some arbitrarily chosen point. But if T happens to be 2, well then, what did we just do? We took OA and we added 2 copies of AB, didn't we? Like twice that amount. And so we're like, how would you characterize that? You might say we're along the line, we're twice as far from A as B is from A, or something like that, right? What if T is -1? Where are we? Yeah, over there. I hate to see a bunch of people motioning. Good job. Yeah, we're on the opposite side. We're the same distance as B is from A, but on the other side, if T is -1, right? And that all just comes from kind of like the visual. I'm going completely geometric on it. You can think algebraically about it too. I'm just thinking, right? Okay, let's try, oh, sorry. There. He's color coding everything. Give him a second. All right, let's try a problem. Sorry. Okay. So now I'm giving you two. Here they are. I'm handing you 2 points, just like I said I would. Let's start with coming up with the equation. Let's do that. So I'm going to choose. And by the way, there's nothing sacred about A being the position vector. You could have made B the position vector and then made a vector from B to A, or however you like. There are actually lots of different options here. You'll see that the parameterization that we come up with, or the vector equation, is not unique. You and your neighbor might come up with 2 equally good parameterizations for the same line. Okay, so let's find that vector equation that we just came up with for this guy. So how do we do it? We go xy is equal to, start with a position vector. You want to do the position vector to C maybe? Just because we like alphabetical order, I don't know. All right, so we'll make this the position vector. And the position vector from 0, 0 to -5, 2 is of course just -5, 2. All right, so that's our position vector. And then we'll do plus t times the direction vector, and we'll use the vector from C to D, how about, right? As our direction vector, CD. So can we just do that in our head quickly? What would that be? From C to D. So we're doing D minus C, right? Head minus tail. So yeah, 1 minus -5 is 6, comma 4 minus 2 is 2. Did everyone catch that? So that should follow nicely with what we just saw on the previous slide, the picture and all that. Position vector first, plus t times the direction vector. Beautiful. Next. All right, so I might call that the vector equation of the line, but let me quickly run through why this is also, like you might be like, why do you keep saying parameterization and vector equation, and like what do those mean? All right, so let me just emphasize like what this is, just to make this clear. This is, remember, this is t times this vector. That's a scalar multiple, so you could write it this way if you like. Agree? Okay. This is the sum of 2 vectors. How do you add vectors? Component-wise. So how do we get -5 plus 6t? 2 plus 2t. So is it becoming clearer why this is like, you could call this the vector equation, but you could also call this the parameterization, right? Where x is equal to what? X is the same thing as -5 plus 6t, just to kind of like bring this all the way back to what we did yesterday here. And y is equal to 2 plus 2t, right? So if you wanted the parameterization, we're splitting hairs here, really, because like really all of these say exactly the same thing, don't they? But I just want to connect this representation with this representation, which are both things we used yesterday. Vector equation, parametric set of parametric equations, cosmetic difference, right? Really the same information, just collected in different ways, okay? Yes, so far so good? So we have this nice little vector function, or parametric function, same thing. You give me a t value, we output a point, x, y. Beautiful. You ready? Keep going here. We got to do answer A and B. Can we give restrictions based on our conversation that we gave a second ago? We had a little conversation about this. What would put us at the point C? What C value? Right, so I think that if t is 0, we're going to be at C. And what puts us at D? What t value puts us at D? 1. And just verify that we're not crazy and actually try it. Like plug in 0 and 1 and see that that does actually restrict us to values along that segment CD, right? So that's just the follow-up on our conversation we had again just a second ago on the last slide. Okay? I mean, just check it out. I mean, and this is maybe the most helpful form up here to plug this into, this first form. If you plug 0 in, it's like super obvious that we get C. Done. And why is it true, like algebraically, that if we plug 1 in, that we get the point D? We can try it. Well, because how did we generate this direction vector? Wasn't it D minus C? So what happens when we add C back to it? Well, of course we get D, right? All right. So, and then what about B? Give the coordinates of a point 2/3 of the way from C to D. How would we do that? Yeah, and by multiply by 2/3, you mean let t be 2/3, and that will generate the point. I don't know, I haven't figured it out yet. But if we plug in 2/3, that'll do it for us, yeah?
I didn't get how to get A.
A? So we're thinking of, like that conversation we just had on the last slide, we're thinking, what are we actually doing? Remember, we have a vector, the position vector, and then we're like adding a certain amount to it. So the position vector, like if we just take the original vector, this is -5, 2 here, and we add 0 of this vector to it, that is, this part is nothing, then if t is 0, we're definitely at the point we started with right here, right? Like plus nothing. If t is 1, then you can just check right now. Plug in 1, see what you get. What is -5 plus 1 times 6? Beautiful, and yeah, likewise, it's 1, 4. And why did that happen? Well, think about the picture again. If you add this thing plus only one of these, you'll be at the point D, because that's like how we designed this thing to happen. Yeah. So what do we get when t is 2/3? I mean, you can plug it in either one here. I'll plug it in maybe down here in the parametric form. I get -1, yeah? -1, comma, 4/3 plus 10/3, yes, 10/3. All right, so that's an interesting question in its own right. Is find the point 2/3 of the way from C to D. That's cool. Good. Now, the reason that we even did this is because you're like, wait a second, I had a perfectly good way in my life. I had a perfectly good way of thinking about lines in 2 dimensions, and I was really happy with it. Why did we need to like lay all of this on top of it? And the answer is because it generalizes really, really well. And not just really well, but like immediately to 3 dimensions, right? So, how do you think this works in 3 dimensions? Well, like I have basically nothing new to say. You just add another component. It's still position vector plus t times the direction vector, except we have a 3rd component. All right, so I'm just going to rewrite this up here, but it's still OP, the vector, x, y, whatever you want to call it, is equal to the position vector plus t times the direction vector, except now we have 3-dimensional things, right? You want to talk about lines in 4 dimensions? Knock yourself out. It's not any harder. We won't, but one could. So, I mean, it's actually a little bit of a challenge to even conceptualize what how you would do this in any other way. What does it even mean to do a line in 3 dimensions? This is a good way to do it. So maybe you don't even need to write that down. I mean, we've listed doing that. Just a little bit of a brain bender to like get our mind around this. Are we really going to be able to think about this, visualize it in 3D? Ooh. It'll be a little rough, maybe, but we'll get there. So I just copied this diagram. Hopefully you're not copying that again from the previous slide, and then the only new thing is this here. And really the only new thing is this. Right? Okay. So, I'm ready to try a problem of the very type that we just did, just with like 2 points with a third coordinate. We'll just try another problem of the type we just did. Yeah. Yeah.
So this is the same with both of them, but OP equals OA plus TAB. Is the equation like the B1 minus A1? Wouldn't that be for B to A or?
No, it's from A to B. We always do head minus tail.
Oh, right.
Yeah, I know that's weird. Okay. Let's try this with 2 3-dimensional points and just repeat the process we just had, right? It says give the vector and parametric equations. Again, we're kind of splitting hairs though, but we'll represent them in those 2 ways just to emphasize. And we'll go a little quicker on this too. So we have x, y, z is equal to, which one do you want to make the position vector? Let's do A, just because we like alphabetical order maybe. Okay. Though it would be interesting for like someone else maybe to use B. Maybe your neighbor does B. And just see that in the end, with this question we're going to get at the end, we're going to maybe all get the same answer, I hope, right? Okay, so we'll use the position vector to A. So it's position vector plus T times direction vector. So are we going to make the direction vector be AB? Okay, so here's OA. And we'll do AB just to follow our notation, I guess. So help me out here. 0 minus 1 is -1. 2 minus -2 is 4. And -5 minus -4 is -1. Check my arithmetic, please. Do you see how that was not very painful after having done the last one, even though we're in 3 dimensions now? Oh. Yeah, it wasn't any more painful. Okay, good. It also said we gave the parametric equations, so let's write those down as well in this form. X equals 1 minus t. Do you see how I'm just skipping the intermediate steps? I think we can see it. Y is equal to this thing plus t times this thing. That's -2 plus 4t. And z is equal to -4 plus -t. How about that? Okay. I want to make sure, I know we're going quick because we have 31-minute period today, and I apologize, but still don't want to lose anyone. Is that good? You like what I put in the 2 red boxes? Again, I'm calling this vector form and parametric form, but please, let's all understand that it really is just cosmetic, isn't it? I mean, they really do communicate exactly the same information, just 2 ways of like kind of thinking about it, maybe. Okay, and then it says determine the point halfway between A and B. So after our discussion on the last one, how might you do that? Set t equal to, 1/2, right? So if t is 0.5, that gives us, you can use any of these equations, whichever form you like. That gives us the point 0.5, comma 0, comma -4.5. By the way, this point that's halfway from A to B, we might also call the midpoint. And I think someone asked you once in your past life, like, what the midpoint between 2 points was. And you had like a midpoint formula, aka like the average, right? If you're ever doing that, can you just verify quickly in your head that this is in fact the midpoint between A and B, using like old school midpoint stuff? Yeah. Just average A, X's and Y's. Because that should all, I mean, everything should work, math should work, so, okay. Hopefully those are the midpoint of each X, Y, and Z sets of coordinates, okay? I mean, obviously this gives us more access to doing more exotic things though too, like the last one we did 2/3. Whoa. You know, but for you, yes. Oh, of course we can do lots of other interesting things. So let's do more interesting things. And we do as much as we can. Let's write an equation. Now we're not like handed 2 points. We're given some more interesting information. Write an equation containing 0, -2, 3, perpendicular to the xz axis, the xz plane. Excuse me. Let's take maybe some visualizations. All right. Okay. What does it mean to be perpendicular to the xz plane? We can draw a little picture here. Where's the x? X, y, z. So the xz plane is like this one here, right? Another way of saying perpendicular to the xz plane would be to say orthogonal to it, or could say like in the direction of y, right? Like you could also, that would be an equally good way to say this. Give me a line that goes through 0, -2, 3, parallel to the y-axis would be a perfectly good way to say this too, if you like. That's a tall order, but can you give me even 1 point on the line besides the one I already have? What must be true? If it's in the direction of the y-axis, what's another point? Just name one. There are an infinite number of them. So, you got another one? Someone?
0, -3.
Yeah. The point is 0, comma, whatever you like, comma 3, right? That is to say, 0 and 3 aren't going to be changing, but y is free to change, right? So yeah, you could make it. What was your number? -3 in here or something? Okay, sure. So there, now you have 2 points. That's great. The other thing to say, though, is that when we come up with these equations of lines, so that'll work. I think you're good to go now. But let me just think like even a little bit higher perspective on this. When we come up with these lines, all we need is some position vector. It doesn't have to be like the position vector. It can be any point on the line. So this one will do. And this can be any direction vector. That is anything that's parallel. Right? Any scalar multiple in that direction of that vector. So all it would take here, maybe we didn't have to come up with another point, is for you to name a vector that's in this direction, in the y direction. How about 0, 1, 0? If you said 0, 2, 0, fine also, right? Does that make sense? Anything at all, 0, anything will work. So yeah, maybe you can just like write that down. It's also fine if you're not like catching this discussion, fine. You can do what we just did, use these 2 points and follow the procedure we just did. Yeah. No. Yeah, so what happens when you subtract these actually? Actually, you happen to pick a point when you subtract these, you'll get this.
Oh, that's the difference.
Yeah, it's the difference. It's the difference, right? The direction vector. So this is good. But like, I just want to emphasize that like there are an infinite number of equally good solutions. Here's another one that's equally good. Here, we're just traveling along the same set of points, just like twice as fast, right? Does that make sense? We like get to a place at a sooner t-value on this line, but it still generates the same exact set of points. Yeah.
So which of those 3 in the second set of points is solidified, and which one's
Solidified.
like the
So
0,
just to be clear again, this is any. I know we said the position vector and the direction vector, but really it's any position vector. That is like this piece here. You could put 0, -3 here if you like. Right, so another good equation of this line would be like 0, 0, 3 plus t times 0, 2, 0. It just doesn't matter, right? Anything on this line will work.
So
Yeah.
for that, it just has to have 0 on both sides.
Yeah, here. Or it could be like 20, right? Doesn't matter. Any scalar multiple will work too. All these are good equations for the line. This can be like, that will work too. Anything. Can you explain why these lines are parallel? Go.
Dot product.
Oh.
You think you got it still?
The one on the right is, they're both are multiple.
What is?
Oh.
X.
What's the language we've been saying? The.
Yeah, the scalar is, I don't know how to word it.
You have it though. Something is a multiple of something. Yeah.
The position vector in the one on the right is a multiple of the position vector in the one.
Good try. I've been calling it the direction vector. Yeah. The direction vectors. This is the part that the position vectors. I'm like, who cares? Who cares? The direction vectors. This is the critical piece because if we move the line in space, who cares? The thing we care about is that the two direction vectors are parallel, and we know that because of what Stella just noticed, and that's they're scalar multiples. So I've said it. I'll try to write it. Since 8, -2, -6 is equal to, what is it? -2 times this. The direction vectors are parallel. Right? And the position vectors just don't matter. So, well, because it's just like asking, it's very, very analogous. I hope maybe you've caught this analogy. It's very analogous to like slope and y-intercept, right? Like this controls the movement, this kind of the slope. That's a way to kind of adjust it a little bit. And this controls the position. If you change the y-intercept of a line, then it's still parallel to what it used to be, right? So you could draw some pictures to give it to yourself if you like. By the way, that makes me think too. Cool. That means like if I had two lines intersected, and someone asked me to find the angle between them, do you think you know how to do that? Take the direction vectors. Find the angle between those. Or someone asked you, are these perpendicular? You might take the two direction vectors and ask if their dot product is 0. All the stuff we know still applies here. The only other thing, if I can fit it in here, is to say something about intersections, okay, between lines. So we find the intersection between these two lines. The first thing I guess that would be like, are these even two lines? So you might have to like stare at them for a second and realize that, oh yeah, x equals t minus 8. Y equals 2t minus 6. And z equals -2t plus 5. Okay, that is a line. I think I get it. Down here, I'm using t as well, but I'm going to swap it out for s just to be clear. Because we're going to say at least, when we mean intersect, we mean, is there ever a point that's on both lines simultaneously? What we don't necessarily need to have happen is that the t and s value be the same at that point. So set up a system of equations. This equals this equals this, and this equals this, and solve. Solve for t and s, find the point. We'll say more tomorrow, or on